Okay, so now we're going to take a look at calculating expected value in a jacks or better hand. And in order to do that, we need to start by actually assigning a value to all the different outcomes. So far, we've talked about the rankings of poker hands, but that doesn't actually put a number to how much the player is going to win or lose if they make a particular hand. Now, when you go to play a game of jacks or better, it must have with it what's called a pay table, and this tells you how much money the player receives for making a certain type of hand. So here's an example of a jacks or better pay table. Per unit wagered, making a royal flush wins the player 800 units, and those units could be dollars, they could be quarters, they could be $10, it could be anything. So for example, if you bet a quarter and you make a royal flush, you'll win 800 quarters, or $200. If you bet a dollar and make a royal flush, you'll make $800. If you bet $5 and make a royal flush, you'll win $4,000, and so on and so forth. So all the way down the line, a full house pays back 9 times the bet, a straight pays back 4 times the bet, all the way down to a pair of jacks or better, which is where the game gets its name, which pays back just 1 times the bet. So if you bet a quarter, you win a quarter, and you break even in the long run. So this means the lowest possible hand to get paid on is a pair of jacks or queens or kings or aces. If you make a pair of 10s, 9s, 8s, 7s, 6, 5, 4, 3, 2s, you don't win anything, you lose. And if you don't make a pair at all, you also lose. Now, this is what's known as a full pay or 9-6 pay table, and it gets the name from this. Let me erase some of my circles here. But it gets the name 9-6 from the 9 units returned for a full house and the 6 units returned for a flush. If the player makes the optimal decision on every hand, then in the long run, this pay table returns 99.54% of whatever the player bets. So, in other words, in the long run, for every $100 wagered, the player would win back $99.54. So, it's not very bad. You don't lose a ton of money playing this game, assuming that you make the optimal decision every single hand. Unfortunately, that's sort of an inhumane task, and most people are going to make mistakes every now and then. We're going to see that just looking at one hand and one possible decision for that hand takes a little bit of time to calculate the expected value. And we're going to look at one of the examples we've already talked about, which is a pretty straightforward hand. As we look at more complicated hands and try to determine the expected value of different plays, then it becomes even more difficult, and trying to calculate the optimal decision in every possible scenario is, almost impossible to do by hand unless you have an infinite amount of time. Fortunately, computers aid us in that endeavor, and through computer simulations, finding the expected value of every possible outcome has been done digitally. The other thing I'll mention is if you were to just walk into a casino and sit down and start playing jacks or better, chances are you're not going to see this particular pay table. There are a lot of variations where casinos will instead pay 8 units for a full house and 5 units for a flush, or even 6 for a full house and 5 units for a flush. And this, of course, brings down the overall return because people are winning less money when making those particular hands. But these are the values we'll use for expected value calculations. And so let's get to, again, one of the situations we've already talked about. So a person playing jacks or better video poker, we're now going to say they're betting $1 on their hand, and they're dealt the hand jack of hearts, queen of hearts, ace of hearts, 7 of spades, king of hearts. So should look familiar. We already calculated the probabilities here. Suppose they hold the jack, queen, king, ace of hearts. What is their expected value? So remember, expected value is the sum of every outcome times the value assigned to that outcome. So the first thing we need to do is break down what are the possible outcomes. If the player holds the jack, queen, king, ace of hearts and it replaces the 7 of spades, the possible outcomes are they draw the 10 of hearts and then they have a royal flush, or they draw a heart other than the 10 of hearts, so they get a flush, or they draw a 10 other than the 10 of hearts, so they get a straight, or they draw a jack, queen, king, or ace, so they make a pair, jacks or better, or none of those things happen. and they don't improve their hand, so they lose. So I'll just say the last outcome is they just lose. And again, we've already calculated each of these probabilities, but we'll go through them again. Okay, so here are all the outcomes, and when trying to calculate the expected value of a certain play, this would have to be the first thing that you do. Think about what cards could come and what type of hands could be formed, and lay out all the different possible outcomes. Now we'll need to find the expected value of each outcome. And again, that's the value of that outcome times its probability. So, first outcome is making a royal flush. Now again, a royal flush pays 800 units, in this case $800. Now since the person paid $1 to play the game, making a royal flush would give a profit of $799. The probability of that occurring, as we worked out before, there are 47 cards in the deck, and one of them is the 10 of hearts. So the probability of making a royal flush would be 1 out of 47. Next, the expected value of getting a flush, if we look to the pay table, a flush pays 6 units. So if we bet 1 unit to make 6 units, then that means the probability, or the value of getting a flush would be plus 5 units. So, and again, units in this case means dollars. So the expected value of a flush would be the value of $5 times the probability of a flush. Now again, there are 47 cards to choose from. There were 13 hearts in the deck, but we are already holding 4 of them, which means 9 hearts remain. One of those hearts is the 10 of hearts that we've already considered, so we need to subtract that out as well, meaning there are 8 cards in the deck that give us a flush, but not a royal flush. You see now why it's important to consider the probability of getting a flush, but not a royal flush, because the royal flush expected value was already included up here. And if we include that card in this probability as well, then that would inflate the expected value. So we do need to make sure that these are all distinct events. They don't overlap at all. Okay, what's the value of making a straight? Well, if we go back to the pay table, a straight pays back 4 units. We paid $1 to play, which means we profit $3 when we make a straight. There are 47 cards in the deck that we could draw. Excuse me. 4 of them are 10s, but one of them is the 10 of hearts. So that leaves 3 10s remaining in the deck that give us a straight, but not a royal flush. Now, the probability of making a pair, and again, since we have the jack, queen, king, and ace, the only pairs we can make are jacks or better. And so if we make a pair with one of those, this pays back 1 unit. We paid 1 unit to play, and that means this is a completely break-even scenario. We paid $1, we won $1 back. So the value of that is 0. The probability of that occurring, we talked about this before, 47 cards in the deck, 3 jacks, 3 queens, 3 kings, 3 aces remaining, which makes 12 total cards that give us a pair. Now, the last option is we don't have any of those things happen. We don't get a royal flush, we don't get a flush, we don't get a straight, we don't get a pair, and so we just lose. This is the outcome that has a value of -1. We paid $1 and we didn't win anything back. Now we have to figure out how many cards meet that event. There were 47 cards total, and we've already considered 12 plus 3 is 15, plus 1 is 16, plus 8 is 24. So 24 cards are already accounted for. 47 minus 24 means there are 23 cards remaining. So 23 out of 47 is the probability of that event. So our expected value then is going to be the sum of each of these terms. 799. Well, actually, let me go ahead and combine them as a single fraction. So the royal flush is 799 times 1, so 799 over 47, plus the flush is 5 times 8, so that's 40 over 47. The straight was 3 times 3, so that's 9 over 47. The pair, again, that was break even, so 0 times anything is 0. And then losing, -1 times 23 over 47. Now we can combine these all into a single fraction over 47. So we have 799 plus 40 is 839, plus 9, Actually, let me go ahead and just write that down so it's easier to follow. So if I put those together, I have 839 plus 9 is 848, and then minus 23 is 825. So we're left with 825 over 47. Now, since we're talking about expected value, I do want to calculate or convert this into a decimal. That decimal is going to represent the actual dollar amount. So 825 over 47 gives us 17.55. So this is approximately $17.55, meaning if we bet $1 in this hand and we made the play of discarding the I forget what the random card was. The seven of spades. So we make the play of discarding the seven of spades. That play has an expected value of $17.55.